All right, so this tutorial we're going to introduce a very important set of rules called Kirchoff's laws that govern how current and voltage must behave in any circuit. Up until this point, we've learned about simple circuit, basically a voltage source, one resistor, and maybe a switch. And we learned about Ohm's law and didn't do much beyond that except for some important concepts. So now we're going to extend our understanding into circuits where there's multiple elements. Our main focus is going to be where there's multiple resistors. But I'm going to start off with an example where we have not only multiple resistors, but we have multiple voltage sources. These things happen in many electronics. We're not going to get too far in the weeds in this one. I just want to show you ultimately where we're going to go, and then I'm going to step back and do notes to introduce the rules to allow us to solve a complex circuit like this. So let me explain a little bit more. So we have three voltage sources, three resistors connected in essentially three loops. A left loop, a right loop, and then an overall loop. And the goal is to figure out what the current is and the voltage drop is across every resistor. Well, if we try to just apply Ohm's law like we did in the simple circuits, we'd find it nearly impossible because it's not really clear which way current is flowing, right? If this is the positive side of this voltage source, is current going this way? Well, you might think so, but then here's the negative side, which is in essence opposed. Oh, I shouldn't say that. That's going with it. So it could continue going through this one because the positives to the negative to the positives. But if I look at this side and this side, I see they're opposed to each other. Positive is facing a positive, so it's not clear how things behave. So in order to ultimately figure this out, I need two general rules. And like I alluded to earlier, those are rules that center on how voltage must behave, which is the law of conservation of energy, and how current must behave, which is the law of conservation of charge. So now I'm going to turn to the notes sheet that you should have that explains Kirchhoff's rules for very simple cases. Okay, I'm going to try to do some examples and really pay attention because it can get confusing at first, but they're not really complicated mathematically. All right, so with that said, let's go to that. So Gustav Kirchhoff was a very important 19th century physicist. He did a lot not only with electricity, but with understanding of light, especially with black body radiation. Okay, so we're going to learn two new rules. We already have Ohm's law. Okay, and they're going to form the backbone for any simple or complex circuit analysis, and that's where we're moving. We're going to, after I go through these basic rules, we're going to start with the simplest complex circuit, a series circuit, then we do parallel circuits, then we're going to do combination circuits. And they're all mostly based on multiple resistors, not necessarily multiple battery or voltage sources. Okay, so we're going to start, and I just said that, we're going to start with series circuits. And I'll explain that. Then you're going to learn about parallel circuits. We'll probably have a FET lab with that, and then combination circuits. And combination simply means it's a combination of series and parallel. Okay, so the first rule we're going to learn, and you want to remember these names, is Kirchhoff's junction rule. And I sometimes abbreviate that KJL. Kirchhoff's junction law or rule, okay? And it's ultimately a statement of the law of conservation of charge. So this is not new physics, it's just an application for a circuit. Okay, it's a very simple statement. For any given junction, the total current coming into a junction must equal the total current leaving the junction. Okay? So before I move on, let's talk about what the heck do I mean by junction. On a schematic, it's usually, but not always, denoted with a dot of some sort. Okay, so let me go to this example right here. Let's say I have a current coming in, and I see an arrow indicating the current is flowing to the right, I1. This point is a junction because the current has multiple paths that it can go down. It can split to here, it can go to I4, it can go to I3. Okay, if I look at this example here where the dots are, these are junctions because current can take multiple paths. And so a junction is essentially where three lines come together and the current can go down one path or another depending on which way it's moving. So it's important for you to identify what a junction looks like on a schematic. Okay, I'll also want you to keep in mind that current can always be calculated using Ohm's law, saying whatever voltage drop there is, let me write that as a delta V, over whatever resistance is at that point. Okay, so we're going to use that to help us understand complex circuits. So let's do some general examples because there's really not much more to do here. Okay, so let me scroll up. So example 1. So let me actually step back a second. So I said this is schematic. You notice there's things missing. They don't show any resistors or voltage sources. So this is just basically a part of a larger schematic. We've zoomed in on a particular part of it, and we're just interested in what's going on in the junctions. So there is a voltage source somewhere. There are resistors somewhere, but we're not interested in them right now. Okay, so I have two junctions, junction A and junction B. And I can ask, what is the magnitude and direction of the current in this part of the circuit? So how would I approach that? Well, I would say that basically the current in any junction equals current out. All right, that's KJL rule, Kirchoff junction rule. So let's look at junction A. I see that the arrows don't mean, I don't want you to think in terms of left, right, up, or down. I want you to think in terms of into the junction or out of the junction. So we can see that coming into A, we have 1.5 amps and 2.7 amps. So coming out of A, right, I have to have the same amount that's coming in. So I've got 2.7 plus 1.5. So for circuit A, right, the in is 1.5 plus 2.7. Sorry, that has to equal the out, which is 4.2. So I've got 4.2 ohms here, excuse me, amps. Now I can look at junction B. So I've got 4.2 coming in. I've also got from I4, 3.3 coming in. So I can say, and I'm going to erase this because I don't have a lot of space. Okay, I can say, here's my in. What's coming in? The current from junction A combined. I've already figured that out. I've got plus I4. That's coming into the junction B, and that has to equal the current going out of junction B, which is just I3. So this we already established is 4.2 plus 3.3 equals I3, and that's going to be 7.5 amps. All right, so that's one simple example of the junction rule. So study that and see if you have any questions before you move on. Okay, here is another circuit I've talked about before. Again, there's voltage source somewhere and resistors. We don't really care about that at this moment. So I want us to write an equation that expresses the junction rule. And again, the junction rule is simply what comes into a junction must equal what goes out of a junction. So simply establish what's coming in and out based on the arrows. So I'm just going to use I's and O's for each one. So if my junction is right here, then I1 is coming in. 4 is leaving it, so that's out. 3 is going away from the junction, so that's out. 2 is going away from the junction, so that's out. So what I can say then is, and there's different ways you can write it, I'm going to say I1, I'm going to call that positive because it's coming in, minus I2, out is going to be negative, minus I3, that's going out, minus I4 has to add up to 0. Okay, so that's another way of looking at the junction rule, okay, is that the total change at a junction must be 0. So I could have just as well said I1 equals I2 plus I3 plus I4. It doesn't matter. So I just want you to be familiar with that way of writing it. Okay, let's go to 3. That's a stranger looking junction, but it doesn't really matter because all we care about is in versus out. So I'm going to go through, here's our junction with the dot. So I5 is in, out, out, in. Okay, so I can write an equation. I'm going to set everything equal to 0. So I'm going to call in positive, so I'd say I1, let's see, I'll just go in order, minus I2, because 2 is out, minus I3, plus I4, plus I5 must equal 0. Okay, so there's a application of that. Now I could actually give values. So let's go through. I want to find what the value is of I2 is, whoops, sorry, given all the others. So I1 is 4 amps, minus I2, which is given as, that's what we're looking for. Okay, so I'm going to put minus I2 minus I3 is 5. I'm not going to put the units anymore. Plus I4, 2, plus I5. I'm going to mess this up. Our name is 3 equals 0. So if I solve for I2, I believe I get 4 amps. All right, I'll let you check that out. Okay, so I'm going to move on to the next rule because I want to try to get this done in 15 minutes. So the next rule is Kirchoff's loop rule. KLR, loop rule. All right, and that's for voltage. So the junction applies a current, loop applies to voltage. You want to remember that. And this is nothing more than the law of conservation of energy, because voltage is associated with energy. So there's two ways of expressing the loop rule. Okay, it says for any given loop, and a loop in a circuit, okay, is going from a positive terminal to the negative terminal of an EMF. An EMF is a fancy way of saying a voltage source. The sum of the voltage, okay, drops must be equal to 0. Okay, so basically when you got a circuit, you have a loop. You have a rise in potential due to the battery, and then you have a drop in potential due to the resistor or resistors. And it should make sense that the total of the drops has to equal the rise. Okay, and put another way, the voltage drops across all resistors along a particular loop must add up to the EMF. An EMF, which is given the symbol epsilon, is the term for the voltage source. Okay, we'll eventually learn to distinguish that between EMF and terminal voltage. And we also want to remember that any drop in voltage across resistor can be applied using, or can be calculated using Ohm's law. Okay, so let's apply it to a circuit like this. It's a little bit more complicated because I want to do Ohm's law on this. So I've got a basically combination circuit. Here is my EMF source right here, 24 volts. And if I follow this from the positive, I want to end up at the negative. So I follow it, I have to go through this guy. Then I can split between these two branches. So that's a parallel branch. Then I can come down, come back together, go through this guy, and I've completed my loop. Okay, so we can ask ourselves, how many loops are there in this circuit? Because each loop, the loop rule has to apply. Well, there are 2 loops. There is the loop that has to go through here, then goes the left branch and then down, and then there is a loop that goes through the right branch and down. Okay, so we are told that the effective resistance of the circuit is 16 ohms. So the sum of all these, I take that back. It's not as simple as 5 plus 4 plus 12 plus 8 adds up to 16. We'll learn how to do that another time. Okay, so we're going to figure out how to do this chart. We're going to go back and forth between Ohm's law and the loop rule, and maybe even a junction rule. So if I know that the total voltage for the circuit is 24 volts, and I know the effective resistance of the circuit is 16 ohms, I know that the total current has to be V over R, okay, which is 24 divided by 16, which is 1.5 amps. Okay, so that's important. So I know I've got 1.5 amps coming out of the battery. And then when it gets to this resistor, well, how much are coming in? 1.5 amps, so what has to be coming out? 1.5 amps. So I know that the current through R1 is 1.5 amps. All right, so I'm applying the junction rule there. Now, when I come through here, I can split. All right, see, I'm running out of time here. So I'm going to stop the tutorial right now because I don't want to get cut off, and I'm just going to start and pick up where I left off here and take maybe another 4 or 5 minutes.